Look at a map of the world. Africa and South America. You see it? They fit together like puzzle pieces. The eastern coastline of Brazil matches the curve of the Gulf of Guinea with a precision that is difficult to dismiss as coincidence. The bulge of West Africa fits into the concavity of the northeastern Brazilian coast. The geological formations on one side match the formations on the other. The same rock types, the same ages, the same fossil species, as if someone took a page and tore it in half. And the two halves have been slowly drifting apart ever since. That is, in essence, exactly what happened. 200 million years ago, these two continents did not exist as separate entities. They were one. And the Atlantic Ocean between them is not simply water. It is a gap that formed when a supercontinent broke apart and its pieces began to move. They have been moving apart at roughly 1 inch per year ever since, approximately the rate at which your fingernails grow. And right now, in East Africa, the same process is beginning again. The ground is cracking. A new ocean is being born. Today we trace that process from beginning to end. Before we continue, please subscribe to this channel. Your support makes this work possible, and there is much more to explore. Thank you. The person who first fully articulated the complete cycle of ocean birth and death was a Canadian geologist named John Tuzo Wilson. In 1966, Wilson published a paper that asked a question no one had quite framed that way before. Do the oceans open and close in a repeating cycle? He had been studying the ancient geological record of mountain belts in eastern North America and Europe, and he noticed something striking. The rock sequences in the Appalachian Mountains in the eastern United States and the Caledonian Mountains in Scotland and Norway showed remarkably similar patterns, similar types of rocks, similar ages of formation, similar sequences of sedimentary and volcanic deposits. The simplest explanation was that these two mountain belts were once part of the same mountain chain, built when an ancient ocean closed and the continents on either side of it collided. The ocean that Wilson was reconstructing, now called the Tethys Ocean, had opened hundreds of millions of years before the Atlantic, occupied roughly the same position between what would become North America and Europe, closed through continental collision to produce the ancient Appalachian Caledonian chain, and then waited while the assembled supercontinent eventually rifted apart along roughly the same scar to form the Atlantic. An ocean opened, closed, and then opened again in roughly the same place. Wilson proposed that this was not unique, that oceans operate on cycles, opening and closing repeatedly over geological time, and that the mountain belts of the world are the record of every ocean that has ever closed. The Wilson cycle. The insight was profound. It meant that the current configuration of continents and oceans is not a permanent arrangement. It is one frame in a very long film. The Atlantic Ocean we look at today is not a permanent feature of the planet. It opened. It will eventually close. And when it does, the mountains that rise where it once was will be the evidence that it ever existed. Every great mountain range on Earth tells the story of an ocean that is gone. Every flat coastal plain tells the story of an ocean that is still here, but may not always be. To understand the Wilson cycle fully, we need to start at the beginning, at the moment when new ocean is born. And we do not need to go back in time to witness this. It is happening right now, in the Horn of Africa, in one of the most geologically active and geologically informative regions on the planet. The East African Rift System is a 3,000-mile-long network of valleys, lakes, and volcanic centers that runs from the Afar Triangle in Ethiopia and Eritrea, southward through Kenya, Tanzania, Malawi, and Mozambique to the coast of the Indian Ocean near Mozambique. It is where the African continent is being pulled apart. The process is not violent by human standards. There is no single dramatic moment when the ground tears open. Instead, over hundreds of thousands to millions of years, the crust stretches and thins. The surface drops into elongated rift valleys bounded by parallel fault scarps, and magma from the mantle below intrudes into the thinning crust and eventually erupts on the surface. The geological environment of the East African Rift looks distinctly different from the flat African plains surrounding it. The rift valleys are linear depressions, bounded by fault escarpments that can rise thousands of feet above the valley floor. The valley floors contain some of the deepest lakes in the world. Lake Tanganyika, at over 4,500 feet deep, is the second deepest lake on our Earth and contains more liquid water than all the Great Lakes of North America combined. These lakes exist because the crust has dropped. They are the first water in a future ocean basin. The northern end of the East African Rift is especially dramatic because it gives us a complete preview of ocean birth at various stages of development simultaneously. The Afar Triangle, the region where the East African Rift, the Red Sea, and the Gulf of Aden all meet, is a triple junction, a point where three tectonic plates are pulling away from each other simultaneously. The Afar Depression is below sea level in parts, a hot, volcanic, brutally inhospitable desert that is geologically speaking one of the most interesting places on Earth. Parts of the Afar have separated so much that oceanic crust, the thin, dense basaltic crust that underlies the ocean floors, is already forming there. The Afar is not a continent anymore. It is a proto-ocean floor. To the north of the Afar, the process is further along. The Red Sea, which separates the Arabian Peninsula from northeastern Africa, is a young ocean in the full geological sense. It has a mid-ocean spreading ridge at its center, producing new oceanic crust, pushing Arabia and Africa apart at roughly an inch per year. The Red Sea is only about 15 million years old. In global geological terms, it is an infant. 200 million years from now, if the Wilson cycle runs its course, the Red Sea might be as wide as the Atlantic is today. The Gulf of Aden, to its east, is doing the same thing, connected to the spreading system of the Indian Ocean. 3 spreading systems, 1 triple junction. The mechanism that built all the world's major oceans, operating in real time. What drives this process? What force is strong enough to tear a continent apart? The answer lies in the mantle, the 3,000-mile thick layer of hot rock that constitutes most of Earth's interior. The mantle is solid. It does not flow like liquid on human timescales, but on geological timescales, it convects. Heat from the Earth's deep interior and from the radioactive decay of elements in the mantle drives slow circulation, like the slow turning of very thick porridge heated from below. Hot material rises, spreads laterally, cools, and sinks back down. The places where hot mantle material rises toward the surface are called mantle plumes. When a mantle plume impinges on the base of the continental crust, it does several things. First, it heats the overlying crust, causing it to expand and dome upward. Rift zones are often preceded by topographic uplift, the crust rising as hot mantle material pushes from below. Second, the heat weakens the crust, making it more susceptible to the tensional stresses that arise from the spreading mantle. Third, the plume drives extension. The lateral spreading of hot mantle material at the base of the lithosphere generates forces that pull the overlying plates outward, putting the crust under tension. Under tension, the brittle continental crust fails by faulting. Normal faults, where one block drops relative to another, cut across the stretched crust, creating the characteristic rift valley geometry, a down-dropped central valley bounded by uplifted fault scarps on either side. The East African Rift Valley, the Rhine-Graben in Germany, the Basin and Range Province of the American Southwest. All of these are rift systems at various stages of development, produced by the same mechanism of mantle upwelling and crustal extension. In a successful rift, one that progresses to ocean formation rather than failing, the crust eventually thins to the point where magma from the mantle breaks through to the surface. The first magmas are typically basaltic, the dark, iron-rich volcanic rock that eventually makes up all oceanic crust. As the rift continues to widen, the margins of the former continent separate. The gap between them fills with seawater from an adjacent ocean, and the mid-ocean ridge system, the submarine volcanic mountain chain that produces new oceanic crust continuously, becomes established. The ocean is born. The Atlantic tells this story in its rock record with extraordinary clarity. 220 million years ago, there was no Atlantic. The supercontinent Pangaea straddled the equator, with North America locked against Europe and North Africa, and South America locked against Africa. The geography was utterly different from anything recognizable today, but the rock record allows us to reconstruct it in remarkable detail. The rifting of Pangaea began approximately 230 million years ago, coinciding with the Carnian pluvial episode and the volcanic activity of the Central Atlantic magmatic province, the camp eruptions that we have discussed elsewhere. The camp eruptions were associated with the initiation of Atlantic rifting. As the mantle plume that drove the rifting first impinged on the base of Pangaea, it produced an extraordinary outpouring of basaltic lava across what is now the eastern United States, eastern Canada, and western Africa, covering an area larger than the contiguous United States in dark volcanic rock. These basalts, called the Newark basalts in New Jersey, the Palisades Sill along the Hudson River, the Watchung Mountains of New Jersey, are the geological fingerprint of the initial rifting event, visible in the modern landscape as dark ridges and outcrops that mark where the first magmas erupted through the tearing Pangaean crust. By approximately 200 million years ago, the rift had progressed to the point where a shallow seaway connected the Proto-Atlantic to the Tethys Ocean to the east. This early Atlantic, sometimes called the Ligurian Tethys, was narrow and shallow, perhaps comparable to the modern Red Sea in width. You could have crossed it in a few days of sailing. The evaporite deposits, massive layers of salt and gypsum that formed in this early Atlantic basin during periods when circulation was restricted and evaporation exceeded inflow, are preserved in the subsurface of the modern Atlantic margins. Salt deposits beneath the floor of the Gulf of Mexico and along the margins of the South Atlantic are the chemical record of that early restricted seaway when the Atlantic was young enough and shallow enough to periodically dry out like an oversized Dead Sea. The spreading continued. North America moved west, Africa moved east, and the gap between them widened at the spreading center. The mid-ocean ridge, the submarine mountain chain where new oceanic crust is continuously produced by the injection of basaltic magma into the widening gap, became established along the length of what would become the Atlantic. New crust is produced here continuously. Magma rises from the mantle, fills the crack that opens between the two plates as they spread apart, cools to form new oceanic crust, and is carried laterally away from the ridge on both sides, like a conveyor belt moving outward in both directions simultaneously. The rate of Atlantic spreading today is approximately 1 inch per year, about the rate at which a human fingernail grows, as mentioned at the start. This is slow by human standards, but rapid by geological ones. Over 100 million years of spreading at this rate, the Atlantic has grown to its current width of approximately 3,000 miles at its widest point. The process is continuous and ongoing. The Atlantic is wider today than it was yesterday, and it will be wider tomorrow than it is today. London and New York are moving apart by approximately the length of your thumbnail every year. The evidence for this spreading is preserved in the oceanic crust itself, in one of the most elegant records in all of geology. The Earth's magnetic field periodically reverses. North becomes south and south becomes north, at irregular intervals averaging hundreds of thousands of years. When basaltic magma solidifies at the mid-ocean ridge, the magnetic minerals in the rock lock in the orientation of the magnetic field at that moment, like tiny compass needles frozen in place as the lava cools. As the oceanic crust spreads away from the ridge, these fossil magnetic signatures are preserved, producing a pattern of alternating magnetic stripes on either side of the ridge. One stripe where the magnetic minerals point toward the current North Pole, the next where they point toward the south, alternating in perfect symmetry on both sides of the spreading center. When oceanographers began mapping the ocean floor in the 1950s and 60s, they discovered these magnetic stripes and recognized immediately what they represented. A tape recording of both the history of the Earth's magnetic field reversals and of the spreading history of the ocean floor. By correlating the magnetic stripes with the independently determined ages of magnetic reversals from continental rock sequences, they could calculate how fast the ocean floor had been spreading and when each stripe was formed. The Atlantic spreading history is written in these magnetic stripes. a chronological record extending back more than 180 million years, preserved in the dark basalt of the ocean floor. Now let us turn to an ocean that no longer exists, because understanding the Atlantic's future requires understanding what happened to its predecessor. The Tethys Ocean was one of the great oceans of Earth's history, and its story is among the most dramatic in the geological record. The Tethys existed for approximately 250 million years, from the late Paleozoic through the Mesozoic and into the early Cenozoic, occupying the broadly equatorial region that separates the northern supercontinent of Eurasia from the southern supercontinent of Gondwana. At its maximum extent, the Tethys stretched from what is now Spain and the Sahara in the west, through the Mediterranean basin and the Middle East, through Central Asia and the Himalayan region to Southeast Asia and beyond. It was a vast tropical sea, warm and shallow in its marginal regions, teeming with life. The Tethys fauna was extraordinarily diverse. Ammonites, the coiled cephalopods that serve as index fossils for Mesozoic stratigraphy, were at their most diverse and most abundant in Tethyan waters. Ichthyosaurs and plesiosaurs hunted in Tethyan seas. Mosasaurs dominated the Tethys in the late Cretaceous. Reef-building rudists, bizarre bivalves that grew in tower-like structures and replaced corals as the primary reef builders for tens of millions of years, thrived in Tethyan carbonate platforms. The carbonate platforms and reef complexes of the Tethys have left their record in the limestone formations of the Alps, the Dolomites, and the Apennines, rocks that were once tropical seafloor, uplifted and tilted and folded into mountains by the very collision that killed the ocean they formed in. The closing of the Tethys was not a single event, but a prolonged process driven by the northward drift of the fragments of Gondwana. As the Gondwana supercontinent broke apart during the Mesozoic, the various pieces, India, Arabia, Africa, Anatolia, Iran, moved northward toward the Eurasian landmass, progressively consuming the Tethys Ocean between them. Subduction zones developed along the northern margin of the Tethys, pulling oceanic crust downward into the mantle and drawing the southern continents toward the north. The most dramatic of these collisions was the meeting of India with Asia, which began approximately 50 to 55 million years ago and is still ongoing. India had been moving northward from its Gondwanan position at extraordinary speed by geological standards, at rates of up to 7 to 8 inches per year, nearly 10 times faster than the current Atlantic spreading rate. This speed was possible because the Indian subcontinent was being driven northward by both the spreading of the Indian Ocean behind it and by the subduction of the Tethys oceanic crust ahead of it. As the Tethyan crust disappeared into the subduction zone, India was pulled forward like a ship being pulled by its anchor rope into a harbor. When the Tethyan oceanic crust between India and Asia was finally consumed, when the two continental landmasses finally came into direct contact approximately 45 to 50 million years ago, the collision stopped being a simple subduction event and became something far more dramatic. Continental crust is too buoyant to subduct. It is lighter than the underlying mantle and cannot be forced downward no matter how much tectonic force is applied. When continental crust meets continental crust at a convergent margin, the result is collision. The two land masses crumple against each other. The crust thickens and mountains rise. The Himalayas are the direct result of the Indian-Asian collision. The Indian subcontinent has been driving northward into Asia for 50 million years, at a rate that has slowed as the collision resistance increased, now proceeding at roughly 2 inches per year, still fast by geological standards. The crust in the collision zone has thickened from a normal continental thickness of 25 to 30 miles to more than 40 miles in Tibet. The Tibetan Plateau, the largest and highest plateau on Earth, roughly the area of Western Europe at an average elevation of nearly 3 miles, is the product of this crustal thickening. And the Himalayas themselves, rising above the plateau in a series of ranges capped by the highest peaks on Earth, are the extreme expression of what happens when two continental plates collide and nowhere to go but up. Mount Everest, the highest point on Earth at approximately 29,000 feet, is composed largely of limestone, rock that formed in the shallow seas of the Tethys Ocean. Marine fossils have been found at elevations above 26,000 feet on the flanks of Himalayan peaks. These are not marine fossils that were uplifted from a nearby sea. They are the remains of organisms that lived in the shallow, warm water of the ancient Tethys, whose carbonate bodies accumulated on the seafloor over tens of millions of years, and which were then uplifted from near sea level to the roof of the world by the same tectonic forces that consumed the ocean they lived in. The highest mountains on Earth are built from the floor of a vanished tropical sea. The Mediterranean Sea, the Black Sea, the Caspian Sea. All of these are remnants of the Tethys. Not the full Tethys, which was thousands of miles wide, but small isolated basins that remained when the main ocean was consumed. The Mediterranean is slowly closing. The African plate is moving northward, subducting beneath southern Europe along the arc systems of the Hellenic Trench and the Calabrian Arc. In perhaps 100 million years, the Mediterranean will be gone, replaced by a mountain chain comparable to the Himalayas running through what is now southern Europe and North Africa. When that happens, the last remnant of the Tethys will have been erased, and the geological record of its existence will survive only in the limestone of the Alps, the shells of Mesozoic ammonites in museum drawers, and the petroleum reservoirs of the Middle East, because the carbonate platforms and organic-rich mudstones of the Tethys are the source rocks and reservoirs for much of the world's remaining conventional oil. Now let us turn to the Pacific, the oldest, the largest, and the dying ocean. The Pacific covers nearly a third of Earth's surface. It is so large that all of the world's continents could fit into it with room to spare. In its center, the Hawaiian island chain sits more than 2,000 miles from any continental landmass, a measure of the Pacific's sheer expanse. And it is old. The oldest surviving Pacific oceanic crust, in the western Pacific near the Mariana Trench, dates to approximately 180 million years. The ocean itself is older still. It is the remnant of Panthalassa, the global ocean that surrounded Pangaea when that supercontinent existed, which makes the Pacific substantially older than the Atlantic. But the Pacific is dying. and the mechanism of its death is visible at its margins. In the Ring of Fire, the chain of volcanoes and earthquake zones that ring the Pacific Basin. The Ring of Fire is not a coincidence of geography. It is a symptom. It is what subduction zones look like. The Pacific Plate and the other plates that make up the Pacific Basin floor are being consumed at their margins faster than new crust is being produced at the East Pacific Rise and other spreading centers. The Pacific is shrinking. The subduction zones around the Pacific are some of the most geologically active places on Earth. The Cascadia subduction zone off the coast of the Pacific Northwest, where the Juan de Fuca plate is diving beneath North America, produces some of the largest earthquakes possible, including magnitude 9 or greater megathrust earthquakes that occur every few hundred to thousand years. The Japan Trench subduction zone produced the magnitude 9 earthquake and tsunami in 2011. The Aleutian Trench, the Peru-Chile Trench, the Philippine Trench, the Mariana Trench, all of these are places where Pacific oceanic crust is being swallowed by the mantle, returning to the source from which it came. The rate of Pacific closure is real and measurable. The Pacific Ocean basin is approximately 400 miles narrower than it was 100 million years ago, based on the difference between what has been produced at the spreading centers and what has been subducted at the trenches. 400 miles in 100 million years. At this rate, in approximately 300 to 350 million years, if current trends continue, which they will not, because plate tectonic configurations change, the Pacific would be completely consumed. More realistic estimates that account for changing tectonic configurations suggest the Pacific closes completely in roughly 250 million years. What happens then? The continents currently arranged around the Pacific Basin will collide. The Americas, which are currently moving westward away from the growing Atlantic, will eventually reach Asia. Australia, which is currently moving northward at approximately 2 inches per year, and will collide with Southeast Asia within the next 50 to 100 million years, will be part of the assembled eastern supercontinent. The Arctic Ocean, which is small and already largely enclosed by continents, may close. And the result, the predicted result based on current plate motions projected forward, is a new supercontinent, Amasia, or perhaps Pangaea Proxima. The name depends on the modeling approach and the specific assumptions about which ocean closes first and how the collision geometry works out. But the broad consensus is that Earth is headed toward another supercontinent in the 250 million year time frame. The details of the assembly matter enormously because the assembly process is not quiet. Every collision produces mountain chains. The collision of the Americas with Asia, if it occurs, would produce mountain chains of extraordinary scale, potentially higher than the modern Himalayas, because the continents involved would be larger and the collision velocities might be higher. A Himalayan-scale mountain chain running from Alaska to Argentina, produced as North and South America collide with Asia, would fundamentally reshape the atmospheric circulation of the Northern Hemisphere, creating massive rain shadows and new desert regions. The uplift of such mountains would drive enhanced chemical weathering, consuming atmospheric carbon dioxide and potentially triggering global cooling. The volcanic activity associated with the closure would be extraordinary. As the Pacific oceanic crust subducts around the margins of the closing ocean, the subduction zones would produce arc volcanoes of the scale seen in the modern Andes and the Cascades, but on a much larger total scale because the subduction zone perimeter would be enormous. The volcanic outgassing would add carbon dioxide and sulfur dioxide to the atmosphere. The tension between the cooling from enhanced weathering and the warming from volcanic outgassing would create climate variability of a kind not seen since the last supercontinent assembly. What happens to life during a supercontinent assembly? The geological record of previous supercontinent formations, particularly the assembly of Pangaea at the end of the Paleozoic, approximately 300 million years ago, is instructive. The closing of the oceans that preceded Pangaea produced the Appalachian and Caledonian Mountains, the Ural Mountains, and other ranges that mark where those ancient oceans once were. The assembly was associated with significant biological disruption. The end Permian extinction, the largest mass extinction in Earth's history, approximately 252 million years ago, occurred when Pangaea was fully assembled. The causes of the end Permian extinction are complex and debated, but the supercontinent configuration contributed by reducing the diversity of coastal marine environments, changing ocean circulation, and perhaps amplifying the effects of the Siberian Traps volcanic event. A new supercontinent in 250 million years would similarly disrupt the pattern of coastal environments that supports much of Earth's marine biodiversity. The closure of the Pacific would eliminate the largest and most diverse ocean basin, with consequences for the organisms that depend on it. The assembly of the continents into a single landmass would create enormous continental interiors, far from any ocean moisture, producing deserts of a scale not seen on the modern Earth. The climate of a supercontinent world is extreme, hot in the interior, stormy at the margins, with seasonal swings that make modern climates look mild. But here is the thing about the Wilson cycle that distinguishes it from mere catastrophism. The assembly of a supercontinent is not the end of the story. It is the middle. Because supercontinents, once assembled, do not stay assembled. They break apart. The same mantle convection that drove the continents together eventually drives them apart again. The same process of rifting and ocean formation that we are watching in East Africa today occurred when Pangaea broke apart, and it will occur when the next supercontinent breaks apart. The cycle begins again. The mechanism of supercontinent breakup is not fully understood, but the leading explanation involves the thermal insulation effect of a supercontinent. The mantle beneath the continental crust loses heat through the oceans. Oceanic crust is thin and conducts heat relatively efficiently. Continental crust is thick and poor at conducting heat. When all the continents are assembled into a single supercontinent covering a large area, the mantle beneath is insulated. Heat from the Earth's interior cannot escape as efficiently, and the mantle heats up. The hotter mantle becomes more vigorous in its convection, producing larger and more active mantle plumes that impinge on the base of the supercontinent, initiating rifting. The supercontinent is destroyed by the very heat it trapped. After Pangaea assembled approximately 300 million years ago, the mantle beneath it heated up, plumes impinged on its base, and rifting began approximately 230 million years ago. The first rift produced the Central Atlantic magmatic province and initiated the opening of the Atlantic. 200 million years of rifting, spreading, and ocean growth later, we have the world we see today. In another 250 million years, after the Pacific closes and the next supercontinent is assembled, the mantle will heat up again beneath the new supercontinent. New plumes will impinge, new rifts will develop, and the cycle will begin again. Wilson's insight was correct. Oceans open and close in cycles. What will the rift that breaks apart the next supercontinent look like? It will almost certainly follow the weakest zones in the assembled supercontinent, the old sutures where the continents were welded together, which are never as strong as the original continental crust. The rift that opened the Atlantic followed, to some extent, the old Tethys Ocean suture. The scar left when a previous ocean closed, and the early North Atlantic continental margins were welded together. The next rifting event will likely follow the sutures of the next supercontinent assembly. There is something almost meditative about this perspective. The Atlantic Ocean, which dominates the western horizon from the east coast of the United States, which was the barrier that separated the old world from the new for so long in human history, which carried the trade winds and the returning westerlies that defined European exploration for centuries, is a temporary feature. It opened. It will close. The process has barely begun. 200 million years of growth, perhaps 200 million years more before it begins to close again, and then millions more of gradual closure. On the timescale of a human life, the Atlantic is as permanent as the sky. On the timescale of the Wilson cycle, it is a passing phase in a 4 billion year story of opening and closing. The Appalachian Mountains of the eastern United States are the remnant of a Himalayan-scale mountain chain produced when an ancient version of the Atlantic, the Tethys Ocean, closed roughly 400 million years ago. Those ancient mountains were once as high as the modern Himalayas. They have been worn down by erosion over 400 million years to the rounded, modest ridges of the modern Appalachians. The oldest mountains in North America, reduced to gentle hills by the patient work of water and ice and wind over geological time. When the Atlantic eventually closes, perhaps 200 million years from now, the mountains that rise in its place will begin the same slow process of erosion. In 400 million years, they will be gentle hills, like the Appalachians are today. And perhaps the people, or whatever beings inhabit this planet then, will look at those gentle hills and wonder what was there before. The Wilson cycle is, at its core, a story about the impossibility of permanence at geological scales. Nothing in the geological world is permanent. The continents move, the oceans open and close, the mountains rise and are ground down. The very rock that constitutes the continents is in constant circulation through the geological cycle, weathered from mountains, carried by rivers to the sea, deposited as sediment, buried, metamorphosed by heat and pressure, eventually return to the surface through uplift, and the cycle repeats. The geologist sees a world in constant flux, changing too slowly for any human lifetime to register, but with the momentum of billions of years behind it. The Atlantic's spreading center, the mid-Atlantic ridge, runs the full length of the ocean, from Iceland in the north to Bouvet Island in the south. At one specific location on the ridge, the island of Iceland has been built up by the combined effects of the spreading center and the Icelandic mantle plume, a particularly hot upwelling that has poured out enough basalt to build the island above sea level. Iceland is the only place on Earth where the mid-ocean ridge emerges above the ocean's surface, visible as a volcanic rift valley running across the island from northeast to southwest. You can stand on Iceland and see the ridge. You can walk across the rift valley that is opening the Atlantic. You can stand with one foot on the North American plate and the other on the Eurasian plate, and feel the ground beneath you pulling apart at the rate of your fingernail growth. And know that in 200 million years, the place where you are standing will be 2 continents instead of 1 island. The story of the Wilson cycle connects directly to the story of life on Earth. Life did not merely observe the opening and closing of oceans, it was shaped by them. The closure of the Tethys and the rise of the Himalayas changed global climates so dramatically that it drove the evolution of grasslands in the late Miocene. The cooling and drying created by Himalayan uplift transformed the tropical forests of southern Eurasia into open savannas. And it was in these savannas that the lineage leading to humans evolved. The Himalayan uplift may have been a necessary precondition for human evolution. The Tethys had to die so that we could live. The opening of the Atlantic separated populations of organisms on either side, driving divergent evolution. The animals and plants of South America evolved in isolation for tens of millions of years, producing the extraordinary South American fauna of giant ground sloths, glyptodonts, terror birds, and many other groups that existed nowhere else. When the Isthmus of Panama formed 3 million years ago, closing the Central American seaway that had connected the Atlantic and Pacific. It triggered the Great American Biotic Interchange, as North American and South American species mixed for the first time. The Wilson cycle shapes the distribution of life as surely as it shapes the geography of the planet. The Wilson cycle is also the mechanism by which the planet manages its long-term carbon budget. The subduction of oceanic crust carries carbon in the form of carbonate sediments and organic material deposited on the ocean floor into the mantle. This carbon is released by arc volcanism as carbon dioxide. The collision of continents exposes carbonate rocks to weathering, releasing carbon dioxide. The uplift of mountain chains drives enhanced silicate weathering, consuming carbon dioxide. The opening of ocean basins creates new shallow water environments, where carbonate-secreting organisms proliferate, drawing down carbon dioxide. The Wilson cycle, operating on 100 million year timescales, is the deepest regulatory mechanism of Earth's carbon cycle, the process that has kept atmospheric carbon dioxide within habitable bounds over billions of years, despite continuous volcanic outgassing that would otherwise have produced a Venus-like atmosphere long ago. Look at a map of the world one more time. Africa and South America. The gap between them, that is the Atlantic Ocean. 200 million years of separation growing at the rate of your fingernails. To the west, the Pacific, ancient, vast, dying. To the east, the Indian Ocean, young and spreading, pushing India northward, building the Himalayas from the bones of the Tethys. The continents arranged around you are not where they always were. They are not where they will always be. They are in motion, driven by the slow circulation of the mantle beneath them, carrying the passengers of the biosphere, including us, on a journey that has been going on for 4 billion years and will continue for billions more. The ocean you see on a map is a temporary thing. The mountain you see on the horizon is made from the floor of an ocean that no longer exists. And somewhere in East Africa right now, the ground is cracking. Just a few centimeters each year, too slowly to see, too slowly to feel. And in 100 million years, if the process continues, there will be an ocean there. Born from a crack in the earth, filled drop by drop with the rain that falls on newly separated shores, growing at the pace of a fingernail until it is as wide as the Atlantic and as old as time seems to those who live beside it. Let us go deeper into the specific geology of the Atlantic opening, because the detail of what happened is more extraordinary than the broad strokes suggest, and because it directly shapes the landscape that millions of people inhabit today. When Pangaea began to rift 230 million years ago, the rift did not open cleanly along a single straight line. Continental rifting is messy. It involves networks of faults, competing rift arms, triple junctions where 3 rifts meet, failed rifts that started and stopped. The initial Pangaea rift produced several competing arms. In North America, the Newark Rift System, a series of elongated basins extending from Nova Scotia to North Carolina, was one arm. The Connecticut Valley, where the Connecticut River flows today, is a rift basin. The Gettysburg Basin in Pennsylvania is a rift basin. The Deep River Basin in North Carolina is a rift basin. All of these are the remnants of the initial Pangaean rifting, the failed or abandoned rift arms that did not become ocean, but that tell the story of the rifting process in their sedimentary and volcanic records. The rocks in these Newark rift basins are extraordinary archives of the Triassic world. They contain the footprints of dinosaurs, the earliest North American dinosaur tracks made in the soft mud of lake margins in the rift valleys as the Triassic world was reorganizing after the Carnian pluvial events. They contain lake sediments with annual layers recording the climate of the early Triassic. They contain the volcanic rocks of the camp eruptions, those dark basalt ridges that run diagonally across New Jersey and Pennsylvania and Connecticut. The rift basins of the early Atlantic opening are a geological window into the Triassic world, and they are visible as landscape features in the modern eastern United States to anyone who knows how to read them. The actual successful rift, the one that became the Atlantic, developed along what is now the eastern seaboard of North America and the western coast of Africa, separating these two regions and creating the continental margins that are now buried under miles of sediment along both coasts. The continental margins of the Atlantic, the transition zones between thick continental crust and thin oceanic crust, record the complete history of the Atlantic opening, from the initial rifting through the establishment of the spreading center to the present day. The continental shelves of the eastern United States and western Africa are among the thickest sedimentary accumulations on Earth. In some places, more than 10 miles of sediment has accumulated since the Atlantic opened, as rivers eroded the Appalachians and carried the material eastward to be deposited on the growing shelf. This sediment contains an extraordinary record of the Atlantic's history. The evaporite deposits of the early restricted seaway at the bottom, followed by the carbonate platform sediments of the Jurassic, when the Atlantic was a warm, shallow, tropical sea, followed by the clastic sediments of the Cretaceous as the Appalachians continued to erode, followed by the deepening sediments of the Cenozoic as the Atlantic widened and deepened. Red bottom to top, the sedimentary record of the Atlantic margin is a biography of an ocean from its first days to the present. One of the most dramatic episodes in the Atlantic's early history is the formation of the great carbonate platforms of the Jurassic. Between approximately 180 and 160 million years ago, when the Atlantic was still relatively narrow and warm, the shallow margins of the ocean supported extraordinary carbonate reef systems, comparable in many ways to the modern Great Barrier Reef, but extending for thousands of miles along the margins of the young Atlantic. These reef systems built up enormous thicknesses of limestone, the remains of corals, rudists, sponges, and other carbonate-secreting organisms that lived in the warm, shallow Jurassic waters. Today, the remnants of these Jurassic carbonate platforms are buried deep beneath the sediment of the continental shelves. But they are not lost. They are the source of much of the petroleum that underlies the Gulf of Mexico and the eastern margin of North America. The organic material in the carbonate sediments, the remains of marine organisms, was buried, heated by the overlying sediment pile, and converted to petroleum and natural gas over tens of millions of years. The oil and gas industry has been extracting this geological heritage for over a century. Every gallon of petroleum from the Gulf of Mexico contains carbon that was fixed by marine organisms in the Jurassic Atlantic, organisms that lived and died when the Atlantic was a young, narrow, warm sea, and whose biological legacy is still fueling modern civilization. The South Atlantic opening is geologically distinct from the North Atlantic opening and tells a different story. The South Atlantic began to open somewhat later than the North Atlantic, approximately 130 million years ago, when South America and Africa began to separate. The initial South Atlantic was extremely restricted, a long, narrow seaway confined between the two separating continents, with limited connection to the open ocean. In this restricted environment, evaporation exceeded input, and enormous thicknesses of evaporite minerals, primarily salt, were deposited on the floor of the young South Atlantic. These salt deposits, some of them more than 3 miles thick, are preserved today in the subsurface of the South Atlantic margins. They are also economically significant. The giant pre-salt oil fields of Brazil, among the largest oil discoveries of the early 21st century, containing potentially billions of barrels of petroleum, are trapped beneath these Cretaceous salt layers. As the South Atlantic widened, the connection to the global ocean improved, normal marine conditions were established, and the distinctive biology of the South Atlantic began to develop. The separation of South America from Africa, completed by approximately 100 million years ago, created an oceanic barrier that isolated the faunas of the two continents. And the subsequent independent evolution on each side of the Atlantic is one of the most striking examples of how the Wilson cycle shapes biological diversity. African and South American mammals diverged from common ancestors after the Atlantic became too wide to cross. Primates, rodents, and several other mammalian groups crossed the Atlantic in the Eocene and Oligocene. Exactly how remains debated, but the most likely mechanism is rafting on vegetation mats carried by ocean currents. Once isolated in South America, these animals evolved independently for tens of millions of years, producing lineages found nowhere else on Earth. The New World monkeys, the prehensile-tailed monkeys of South America, diverged from African primate ancestors after crossing the Atlantic and have evolved independently ever since. The caviomorph rodents, the group that includes capybaras, guinea pigs, and chinchillas, arrived in South America from Africa and diversified into dozens of ecological roles unavailable elsewhere. Now let us consider what the geological record tells us about the sutures, the scars left by previous Wilson cycles. Because these sutures are one of the most powerful tools geologists have for reconstructing past oceans and past continental configurations. The basic principle is simple. When an ocean closes, the oceanic crust that made up its floor is subducted and mostly consumed, but not completely. Small slices of oceanic crust, called ophiolites, are sometimes scraped off the descending plate and plastered onto the margin of the overriding continent, preserved as strips of dark basaltic and ultramafic rock within the continental crust. These ophiolites are geologically distinctive. They have the characteristic rock sequence of oceanic crust, from ultramafic mantle rocks at the bottom through basaltic oceanic crust to seafloor sediments at the top. And their presence in a mountain belt is a reliable indicator that an ocean once existed there. The Appalachian Mountains contain ophiolites. The Urals contain ophiolites. The Alps contain ophiolites. The Himalayas contain ophiolites. Every major mountain belt on Earth contains fragments of oceanic crust that were preserved when the ocean those mountain belts replaced was consumed. These ophiolites are geological relics of vanished oceans, preserved like insect specimens in amber within the mountain belts that mark where those oceans once were. By identifying ophiolites in ancient mountain belts and determining their age, geologists can map the history of ocean opening and closing going back hundreds of millions of years. the geological record of the Wilson cycle extending deep into the Paleozoic and beyond. The Iapetus Ocean, the predecessor to the Atlantic, which Wilson himself studied, closed approximately 420 million years ago during the Caledonian-Akkadian orogeny, producing a mountain chain comparable to the modern Himalayas, running through what is now Scotland, Norway, Newfoundland, and New England. The ophiolites of this closure are preserved in the geological terrains of Newfoundland and the Scottish Highlands. The suture zone, where the two continental margins of the Iapetus collided, where ancient North America met ancient Europe, runs through eastern Newfoundland and is visible in the geological map as a zone of distinctive rock types that mark the collision boundary. Subsequently, the Reich Ocean, another Paleozoic ocean, closed to produce the Hercynian mountain belt that extended across what is now southern Europe and eastern North America. And this closure welded all the northern continents together as part of the process that produced Pangaea. The Hercynian mountains have been largely eroded away over 250 million years of weathering. But their roots, metamorphic and granitic rocks formed during the deep crustal thickening of the collision, are exposed in the Massif Central of France, the Ardennes of Belgium, the Bohemian Massif of Central Europe, and the ridge and valley province of the Appalachians. Go back further, and the record becomes less complete, but no less real. The Caledonian and Hercynian orogenies were themselves preceded by earlier Wilson cycles. The Grenville orogeny, approximately 1 billion years ago, produced mountains from the collision of continents before any of the current oceans existed. The Trans-Hudson orogeny, approximately 1.8 billion years ago, was the suture left when two ancient continents collided to form the core of what would eventually become North America. Each of these ancient orogenies marks a closed ocean. Each closed ocean was preceded by an open ocean. Each open ocean was preceded by a rifting event, and each rifting event destroyed a previous supercontinent. The Wilson cycle has been running for at least 2 billion years, and probably much longer. This means that the Atlantic is not merely the product of the rifting of Pangaea. It is the product of the nth iteration of the Wilson cycle, where n is a number that we cannot determine precisely, but that is certainly more than 5 and possibly much more. The Atlantic opened where it did, roughly following the suture of the old Iapetus Ocean, because old sutures are weak zones in the crust, preferentially exploited by new rifts. The Atlantic is the latest expression of a pattern of opening and closing that has been using roughly the same geographic zone for hundreds of millions of years. The ocean that is here today is not the first ocean to have been here. It may not be the last. There is a specific and striking piece of evidence for this recycling of rift zones that deserves attention: the matching geology of conjugate continental margins. The term conjugate refers to the two sides of a rifted ocean that were once joined. The eastern coast of North America and the western coast of Africa are conjugate margins. They were once the same landmass, and they preserve mirror image records of the rifting event that separated them. The continental margin of West Africa shows rock sequences, fault patterns, and sedimentary records that match their counterparts on the eastern North American margin in precise detail, like two halves of a torn document that can be matched along the tear line. When geologists fit the conjugate margins together by restoring the Atlantic's spreading, the match is extraordinary. The geological structures on one side align perfectly with structures on the other. The ancient mountain belts of West Africa align with their counterparts in the southern Appalachians. The Precambrian rock provinces of the West African Craton align with the Precambrian rocks of eastern North America. The suture zones, the ophiolite belts, the sedimentary basin sequences, all of them match because they were the same geology before the Atlantic opening separated them. The precision of this match is one of the most powerful demonstrations of plate tectonics available in the geological record. The future of the Wilson cycle, the closing of the Pacific and the assembly of the next supercontinent, is not merely geological speculation. It is a projection of measured current plate motions into the future, and its broad outlines are as well constrained as many longer-term scientific predictions. Australia is currently moving northward at approximately 2¼ inches per year. At this rate, it will collide with Southeast Asia within the next 40 to 60 million years, closing the shallow seas between them. The subduction zones around the Pacific are currently consuming approximately the same total length of oceanic crust as new crust being produced at spreading centers, with a slight net deficit. The Pacific is slowly shrinking. The Americas are moving westward relative to the Pacific plates, continuing a trend that has been operating for tens of millions of years. These trends, projected forward, produce supercontinent models. The two most widely discussed models, Amasya and Novo-Pangaea, differ in the specific geometry of the assembly, but agree on the basic mechanism and timing. Both predict a supercontinent in roughly 200 to 300 million years. Amasya has the Americas closing the Pacific and joining Asia across the northern hemisphere, with the Atlantic persisting or closing through the Arctic. Novo-Pangaea has the Atlantic closing and the Pacific closing simultaneously, with all continents converging in a single assembly. The specific prediction depends on which ocean closes first and how the tectonic forces balance out. And these details cannot be predicted with confidence that far in advance, because small current uncertainties compound over hundreds of millions of years. What both models agree on is that the current configuration of the Earth's surface is temporary. The Atlantic will not always be there. The Pacific will not always be there. The Himalayas are still rising. The Mediterranean is still closing. The East African Rift is still opening. The planet is in the middle of a cycle, not at a stable endpoint, and the direction of the next major reorganization is already determined by the physics of plate tectonics. It just plays out over timescales that make human history look like an eye blink. The Wilson cycle teaches something important about how to think about the world at large scales. The things we think of as permanent, the continents, the oceans, the mountain ranges, are not permanent. They are processes, not things. The Atlantic Ocean is not a feature of the planet in the way that the mass of the planet or the chemical composition of its rocks is a feature. The Atlantic is a stage in a process that has produced dozens of oceans before the Atlantic and will produce dozens more after it. The Appalachian Mountains are not a permanent feature of North America. They are a stage in a process that will eventually erase them and replace them with something else. This perspective is not nihilistic. The Atlantic is real and beautiful and important right now. The Himalayas are real and magnificent and consequential for the climate and hydrology of half of Asia right now. The East African Rift is producing extraordinary geological and biological diversity right now, in real time. The fact that these features are temporary on geological timescales does not diminish their reality or their importance at the timescales relevant to life and human civilization. But it does place them in context. And the context of the Wilson cycle is one of the most powerful perspectives available for understanding what this planet actually is. Earth is not a stable platform for life. It is an active, churning, self-reorganizing system in which the very ground beneath our feet is in motion. The oceans are opening and closing. The mountains are rising and falling, and the carbon cycle is regulated by processes that operate on timescales of hundreds of millions of years. Life evolved on this dynamic platform, was shaped by it at every stage, and is, in a sense, a part of the system. An active participant in the geochemical cycles that regulate the planet's climate and chemistry. The Wilson cycle is not something that happens to life. It is part of the same interconnected planetary system that makes life possible. The Wilson cycle is not a metaphor. It is the operating system of this planet, the mechanism by which it recycles its crust, regulates its carbon, and maintains the conditions for life. Understanding it changes how you read every landscape you will ever see. The mountain is a closed ocean. The coastal plain is an ocean waiting to open. The Rift Valley is a future sea. There is one dimension of the Wilson cycle that we have not yet fully explored, and it is perhaps the most important for understanding why the cycle exists at all: the deep relationship between plate tectonics and water. Water is the lubricant that makes plate tectonics possible. This is not metaphor, it is physical chemistry. The rocks at subduction zones behave very differently when wet versus when dry. Water lowers the melting point of mantle rock, enabling the arc volcanism that is characteristic of subduction zones. Water weakens the rocks at plate boundaries, allowing them to deform plastically rather than simply fracturing. Water enables the serpentinization of mantle rock, producing the serpentinite that facilitates the sliding motion of plates at fault zones. Without water cycling through the subduction system, plate tectonics as we know it would not operate. Venus almost certainly does not have Earth-style plate tectonics. Venus has lost its water. The connection is probably not coincidental. The dry, hot Venusian lithosphere is too strong, too rigid, too resistant to deformation to break into mobile plates and subduct. Instead, Venus has a single unbroken lid over its entire surface, punctuated by large volcanic structures that release heat episodically, but without the continuous recycling of plate tectonics. The absence of water may be responsible for the absence of plate tectonics on Venus. And the absence of plate tectonics means no Wilson cycle, no carbonate silicate thermostat, no long-term climate regulation, and no mechanism to prevent the runaway greenhouse that has made Venus the inferno it is today. Mars, as we have discussed, lost both its water and its plate tectonics. The small early Mars may have had some form of plate tectonics early in its history. The magnetic striping preserved in the southern hemisphere of Mars resembles the magnetic anomalies of Earth's ocean floors, suggesting that spreading and subduction may have operated for a brief period. But Mars lost its water, cooled quickly because of its small size, and the plate system locked up. Without water to lubricate it, and without heat to drive it, Mars's tectonic activity ceased, and with it any possibility of a Wilson cycle or long-term carbon cycle regulation. Earth's Wilson cycle and Earth's ocean are therefore not merely connected, they are co-dependent. The ocean enables the Wilson cycle through water lubrication. The Wilson cycle maintains the ocean by regulating the long-term carbon budget that prevents runaway greenhouse warming. Each requires the other. Remove the ocean and you remove the lubricant for plate tectonics, which eventually stops the Wilson cycle, which stops the carbon thermostat, which allows carbon dioxide to accumulate until the planet converges on Venus. Remove the Wilson cycle, stop plate tectonics, and you remove the carbon thermostat, which allows carbon dioxide to accumulate until the planet likewise converges toward the Venusian end state. This mutual dependence is part of why Earth has been habitable for 4 billion years. The two systems, the hydrological cycle and the tectonic cycle, have been operating together, each stabilizing the other, forming a coupled system whose robustness comes precisely from the tight feedback loops that connect them. Interrupt either one long enough and the other eventually fails, and with it the conditions for complex life. The stability of Earth's climate over geological time is not the result of any single mechanism, but of the integrated operation of multiple mechanisms that reinforce each other. The mid-ocean ridge system, the product of the Wilson cycle, is itself one of the most important regulators of ocean chemistry. Seawater that circulates through the hot rock of the ridge crest is chemically modified. It loses some dissolved components and gains others, the specific exchange depending on the temperature and the mineralogy of the rock. This hydrothermal circulation is a major control on the chemistry of the ocean, particularly on the concentrations of certain trace metals and on the sulfur and carbon budgets. Remove the mid-ocean ridge system, and the ocean chemistry would change in ways that would affect its biological productivity and its capacity to regulate atmospheric composition. The spreading rate of mid-ocean ridges also matters for global climate on geological timescales. When the ridges spread fast, they produce more volcanic rock and inject more carbon dioxide into the ocean atmosphere system. They also produce higher ridges, Fast-spreading ridges are broader and more voluminous than slow-spreading ones, because the hot rock has less time to cool before being carried away from the ridge axis, and higher ridges displace more seawater, raising global sea levels. The Cretaceous, when sea levels were significantly higher than today, and much of the continental interiors were flooded by shallow seas, corresponds to a period of elevated spreading rates in the global mid-ocean ridge system. The Wilson cycle, therefore, operates on multiple timescales simultaneously. The opening and closing of individual ocean basins occurs on timescales of hundreds of millions of years. The production of individual magnetic stripes at the mid-ocean ridge occurs on timescales of hundreds of thousands of years. The hydrothermal circulation of seawater through ridge crest rocks occurs on timescales of years to centuries. The subduction of carbon-bearing oceanic crust and its return through arc volcanism occurs on timescales of millions of years. All of these processes are part of the same connected system, operating at different rates, but all connected through the physics of plate tectonics and the chemistry of water and rock. Standing back from all of this detail, what is the Wilson cycle, ultimately? It is the mechanism by which this planet maintains the conditions for life over geological time. It is the thermostat of the Earth's long-term climate, the recycler of the planet's carbon, the lubricant of the geological machine, the engine of biological diversification through the creation and destruction of habitat. It is the process that built every mountain, shaped every coastline, determined every ocean, and created the geographic context in which every evolutionary adaptation in the history of life occurred. It is also, in a quiet way, one of the most profound demonstrations of the interconnectedness of systems. The ocean and the tectonic cycle are connected. The tectonic cycle and the carbon cycle are connected. The carbon cycle and the climate are connected. The climate and the biological world are connected. And the biological world, through its effects on weathering rates, carbon burial, and ocean chemistry, feeds back on the carbon cycle and the climate. Every one of these connections runs in both directions. Every system affects every other system. The Earth is not a collection of independent processes, but a single integrated machine in which everything depends on everything else. The Wilson cycle is one visible expression of this integration, the most dramatic and most obvious one, because it operates at the scale of continents and oceans and is readable in the rock record going back billions of years. But it is part of a larger whole that includes the water cycle, the carbon cycle, the biological evolution of life, and the long-term evolution of the sun. All of these processes are operating simultaneously on the same planet, interacting with each other, each one influencing and being influenced by all the others. Look again at Africa and South America on the map. The gap between them. The puzzle piece fit that anyone can see. That gap is the Wilson cycle made visible, the current phase of a process that has been running for billions of years and will continue for billions more. The Atlantic is not where it has always been. It is where the process put it this time around. and the process will put the next ocean somewhere else, or perhaps in the same place. The Wilson cycle is agnostic about geography. It just follows the heat and the weakness in the rock. The Earth does not care about the Atlantic. It does not care about the Himalayas or the Appalachians or the Pacific or any specific configuration of land and sea. The Earth cares, if we can use that word about a geological system, only about maintaining the conditions under which its internal heat can escape and its surface chemistry can remain regulated. The Wilson cycle is the mechanism by which it does so. Everything else, continents, oceans, mountains, life itself, is a passenger on that mechanism, shaped by it, dependent on it, unable to exist without it. The ocean in front of you, wherever you are reading this, is temporary. The ground beneath your feet is moving. The mountains on the horizon are either rising or eroding. And somewhere in East Africa, a crack is opening, slowly, invisibly, at the pace of a growing fingernail, that will become, in time measured not in human lifetimes but in planetary ones, a new ocean, born from the same process that built everything you see, running the same cycle that has been running since before any complex organism existed to witness it. The Wilson cycle: birth, growth, maturity, closure, collision, and again. The planet does not rest. The cycle does not end. And the ground beneath your feet, however solid it may feel, is moving.